Hello and welcome. Today we're going to talk about an example separation of variables solution. In a previous video, we talked about, we showed you the general theory and approach of separation of variables for solving PDEs, and we gave one simple example where that was weaved into the video. In this one, we're going to give one solution straight through, start to finish, and show it to you a little bit more quickly. All right, so let's talk about what we're doing here. So the example we're going to give you, of course, is the heat equation. And it's going to be UT is equal to 3UXX. Of course, it's going to be linear, homogeneous. And so it's going to be separable. That's what we need. And our boundary conditions, they're going to be no flux. So we know that no flux means that negative Kc, the heat conductivity of the spatial derivative of temperature, has to be equal to 0 at the boundaries. In this case, we're going to go from 0 all the way up to 5. Okay? And all that means is that I can write the boundary conditions very simply as going to be ux of x comma t. Sorry, back up there. 0 comma t is equal to 0. And it's also equal to ux at 5 comma t. All right, so those are our boundary conditions written more simply. And all that means, of course, is the heat flux at the endpoints is equal to 0. All right, so the first step, and before we talk about that, though, we have to talk about initial conditions. So in this case, we're actually going to do two initial conditions. We're going to do A and a B initial condition. We'll call them A and B. And the first one will be 3 cosine 2x over 5, or 2 pi over 5x, plus 2 cosine of 8 pi over 5x. Okay? So that will be my u of x comma 0 initial condition. And the other one I'm going to give here is just going to be 1 plus x. That will be the initial condition. So we'll explore both initial conditions at the end. You don't have to worry about initial conditions till the very end. So I thought it would be worthwhile to look at two different initial conditions because you're going to see two different structured solutions in these particular cases. All right. So the first step, of course, is to separate. So we're going to take u of x comma t and set it equal to p of x times q of t, and then plug in. So in this case, it's going to be ut is equal to 3uxx. That becomes p times q. Take the time derivative times 3 of p times q of the space derivative. And then what you get there, of course, is the p of x comes out, and you get q prime of t. And that's equal to 3 q of t times p double prime of x. And then, of course, what we're going to do is divide everything by 3q times p, like that. And we get q prime over 3q is equal to p double prime over p. And it should be noted that the 3 could go anywhere, but I like to keep the 3 with the time equation, and you can see why that is as follows. All right, so of course we know that anytime you have two functions of two different independent variables and they're equal to each other, because x and t are completely independent, I can choose x to be lots of different things, and I can pick t to be lots of different things. But the only way two functions of two independent variables could be equal to each other is if they are equal to a constant. If they were anything else, if the functions varied at all, there's no way you could control how they varied. All right, so let's now see what's going on here, and the next phase of the problem, of course, is going to be the eigenfunctions. So that's going to be p double prime is equal to lambda p. All right, we're going to go to the next page for that. And we have p double prime I'll just write it this way. P double prime is equal to lambda p. But then the boundary conditions, they're spatial, so they go with the spatial function. It's going to be P single prime of 0 is equal to P prime at 5 is equal to 0. And these are those no flux boundary conditions. All right, so let's solve this eigenfunction problem. It should be pretty straightforward. What we're going to do is, of course, have those cases. So the cases, of course, are lambda positive. It turns out there are no solutions for this. There's no solutions here. We won't get into this video why that's true, but you can go ahead and check for yourself if you want. The second case is lambda is equal to 0. Well, let's do this one really quick. That makes P double prime equal to 0. If I just look at the eigenfunction problem, that's what you'd get. Of course, I can anti-differentiate like that. And then if I anti-differentiate again, I get C1x plus C2. But then, of course, I need to check the boundary conditions. And I get P prime of x is equal to C1. So that means P prime at 0 is equal to 0, which is equal to C1, which is equal to P prime at 5. All right, so that means, of course, that C2 is a free parameter. It's unconstrained by the boundary conditions. All right, so that means that P of x can be equal to the function 1, a constant function. Okay, and that goes along with lambda 0 is equal to 0. So I'm going to call this P0. So our first eigenfunction is just the constant function. Great. All right, so now we have to check the lambda is less than 0 case. Now, all right, and so that we get P double prime is equal to lambda P, okay? And in this particular case, if we have the characteristic equation, we're going to get r squared is equal to plus or minus root lambda. Lambda is less than 0. So what we always do is let omega equal root negative lambda. This is always the trick we use, in which case r squared is equal to oh, sorry, I made a little mistake here in my notation. That means that r is going to be equal to plus or minus root lambda. Okay. So here we're going to have r is equal to plus or minus I omega. And here omega is going to be a positive parameter like that. In which case we're going to get our general solution. P of x is equal to C1 cosine omega x plus C2 sine omega x. So that P prime of x is going to be, of course, equal to omega. That comes from the chain rule times negative C1 sine omega x plus C2 cosine omega x. So if I go P prime at 0, that's going to be equal to omega times negative C1 times 0 plus C2 times 1, and that's equal to 0, which means that C2 has to equal 0. Great. So now P prime, if I evaluate it at 5, now, of course, what this means, this C2 means that this whole term right here, that's gone, and so is this one there. So the only thing left to look at are the cosine terms. So if I put this down here, I get omega times negative C1 times sine times omega times 5, and that whole thing has to equal 0. Omega is greater than 0, of course. C1 can't be 0 if it's going to be a free parameter. It can't be a trivial number, which implies that sine 5 times omega is going to be equal to 0. Okay, this looks good. So of course that happens when 5 omega is equal to n pi, for n going from 1, 2, 3, 4, and up forever. What's really important is always start at the right point. That's the correct starting point. So what we find, of course, is then that Pn of x is going to be equal to, again, this goes along with that, cosine of n pi. So remember, omega is equal to n pi over 5 times x. And lambda, of course, is going to be equal, lambda n is going to be equal to negative n pi over 5 quantity squared. And that's going to start from n equals 0, 1. It starts at n equals 1, 2, 3, and 4. It starts at 1. So there's our eigenfunctions for our problem. Okay. All right, so we found our eigenfunctions. And remember, we have to remember the 0 one as well. We have both of these that we have found, and we need to remember both of them. The next thing to do now is to solve the Q equation. So that's, of course, going to be Qn prime is equal to 3 times lambda n times Qn, right? So this is for every n. Okay, it goes from 0, 1, 2, 3. So here we started at 0 because we know that lambda 0 is equal to 0 as well, right? So let's look at that 0 solution here. So of course that means Q0 of t has to be equal just to 1, the constant solution. But actually any free parameter, I'm going to call that A naught, okay? Okay, so any number can be a solution there. So that's for the lambda equals 0 solution. For the other ones, that's going to give exponentials. That'll give exponential solutions, so it's going to be Qn of t is equal to An. Again, that's that free parameter that comes from the general solution to differential equations, like that. Okay. So there are our solutions, and as well Q0 of t. We should write that one again. That'll be just A0. All right, so there we go. And this is true for, again, for n is equal to 0, 1, 2, 3, up forever. Okay, great. Now let's put this all together. We're going to construct the general solution. The general solution, we'll call it U general of x comma t, is going to equal the sum, starting at n equals 0 and going up to forever, of the un x comma t, which is going to be written as the sum n goes to 0 up to infinity of qn of t times pn of x. I can write it as follows. We know the 0 solution is just going to be the constant, so we can just write that as A0. And then we're going to start our sum at n equals 1 and go up to forever. And we're going to have that an, that free parameter there, e to the negative 3 times n pi over 5 quantity squared times t times cosine of n pi over 5 times x. All right, so this is our general solution to our heat equation PDE with zero flux boundary conditions. All right, so the final step, of course, is to incorporate boundary conditions to find particular solutions. So let's look at that the first initial condition. So what we had was u of x comma 0 was equal to 3 cosine of 2 pi over 5x plus 2 times cosine of 8 pi over 5x. Let's set these equal. So now we have to take the u general and evaluate it at time equals 0, and we're going to get A0 plus the sum n equals 1 goes up to forever of an. And notice here that the exponentials, when you evaluate t at 0, become 1. So we just get this. All right. So clearly here, this is a cosine series. All right. But we should be able to read off the things. First off, we can see that a0 is equal to 0. a1 is equal to 0. But a2, if you note here that we have a 2 there, that's clearly our n equals 2, it has a coefficient of 3, so we can write 3 right there. And then, of course, a3 is equal to 0, a4 is equal to 0, and so on until you get to a8. And now if I look at a8, so there is n equals 8, and it has a coefficient of 2. a8 has a function of 2, is the constant 2. And of course the an is equal to 0 for all else. Okay, so let's see if we can summarize that. We should be able to write that out now, that u particular, x comma t then, is going to be 3 times e to the negative 2 pi over 5 quantity squared. There's a 3 out there from the diffusivity constant times t times cosine of 2 pi over 5 times x plus 2, right? And that's going to come from that a8 coefficient, e to the negative 3 times 8 times pi over 5 quantity squared times t times cosine of 8 pi over 5x. So that is our answer to the problem involving the first initial condition. Okay, so in the next problem, what we're going to do now, we're going to do that second initial condition. All right, for this one, what we have here is that u at x comma 0 was equal to 1 plus x. And that's going to be equal to, again, a naught plus the sum, n equals 1, goes up to forever of a n times cosine of n pi over 5 times x. Right. So clearly we're going to have to use the cosine series formula in order to solve. Okay, so that should be pretty straightforward. So a naught, of course, is going to be equal to 1 over 5 times the integral from 0 to 5 of 1 plus x dx. And that's going to be 1/5 times x plus x squared over 2. And then we evaluate at 0 up to 5, and we're going to get that being 1/5 times 5 plus 5 squared over 2. And then we're going to get 1 plus 5 over 2 when we multiply in the 1/5. And that, of course, is going to be 2 over 2 plus 5 over 2, which is equal to 7 halves. So that's my a naught parameter. All right, so I found my first coefficient. The second coefficient is going to be an is equal to 2 over 5, 0 to 5, of 1 plus x times cosine of n pi over 5x dx. So we have to note something, that that's actually the cosine of 0 pi over 5x function, and that's going to be, of course, orthogonal to all the others. So we can rewrite this as 2/5 0 to 5 of x cosine of n pi over 5x dx. Because that term, that number 1 there, that function 1, is orthogonal to all the others. So we don't need to worry about that one anymore. Okay, so let's now compute this fully. Okay, so Actually, let's check. Is that, now I'm making a mistake here. If I have 0 to 5 of cosine of n pi over 5 times x dx, is that true? Is that, so that'll be sine of n pi over 5 x divided by n pi over 5. If I evaluate it 0 to 5, that of course is equal to 0. Yes, indeed, that is true. Okay, so there we go. This is what we need to compute. Now we're going to know the antiderivative. Okay, so you can find this with Wolfram alpha, or if you do a little work, a little integration by parts, but I'll just give it to you. That's going to be equal to n pi times 5 times x times sine of n pi over 5x plus 25, 5 squared basically, times cosine of n pi over 5x, all over pi squared n squared. All right, so when I compute this integral here, so again, I'll circle what I'm going to put down there. I'll put it over here. That's going to equal 2/5, and we're going to evaluate that expression here. But note that the sine term, that part, when I evaluated it 0 and 5, it's going to disappear. So what I'm going to do is just write down, this is going to be 5 squared times cosine of n pi over 5x, all over pi n squared, and we're going to evaluate that at 0 to 5. That's going to give me a, first off, that 5, that can be pulled out, and we're going to just have a 10, okay? And now we're going to have a cosine at n pi minus 1 all over pi squared n squared, like that. So remember that cosine of n pi, that's going to equal -1 to the n power, right there, okay? So one way we can write an is equal to -20 over pi squared n squared, and this is for n that's odd, and be 0 for n being even. Okay, so that's a good way to write this. Let's now, but I'm going to convert this. Let's say that now if I want to just get the odds, if I have to do a of 2k minus 1 is going to be equal to -20 over pi squared times 2k minus 1, and k is going to go from 0, it'll go from 1, it'll go from 1 to 2 to 3 to 4, and so on and so forth. And that gets just the an odd coefficients. So to put this all together, we can write now that u particular of x comma t is equal to 7/2, that's that a naught term, plus the sum of k going from 1 up to forever of -20 over pi squared times 2k minus 1 quantity squared, e times e to the -3 of 2k minus 1 times pi over 5 quantity squared times t times cosine of 2k minus 1 times pi over 5 times x, like that. That is the final solution. This is going to be an infinite series solution for the initial condition u of x comma 0 is equal to 1 plus x. Okay, so I hope you enjoyed watching that thing start to finish, all of the parts for two different initial conditions. In one initial condition, we could just examine the terms term by term and kind of infer what the values are. In the others, of course, we had to come up with an infinite series solution involving computing all of those Fourier integrals in order to find the Fourier coefficients. I hope that shows you a top to bottom solution to a PDE. I'll see you in another video.